In this question, we've got Mr. Jack swimming across a river. So we can picture, I don't know, here's a river. He swims at 6.5 meters per second. He's aiming north. Let's put a little north compass up here. He aims at a tree. Okay, so let's imagine right here is this tree. It's a beauty. Oh yeah. Mr. Jack, let's say, starts here. He aims directly north and he's aiming at a tree. Okay, so Mr. Jack starts here. He's going to aim this way, so he's going to swim this way. The river's 45 meters wide, so 45 meters. The river flows at 12 meters per second. How long does it take him to cross the river? Okay, so let's picture this. Here's Mr. Jack aiming this way. Let's make this just a little bit longer, and the river flows this way. Okay, so what we've got is, and then how long does it take him to cross the river? How far is he in? What's his velocity? Let's just go through and kind of do our subscript equation. What we've got is velocity. I'm going to think of kind of the end result. So what we've got is Jack to ground. That's kind of what we're thinking about. What we're actually given, though, is Jack to water. So how fast does Mr. Jack swim relative to the water? That's 6.5. We've also got how fast the water flows. So velocity of water to ground. So here's our subscript equation. J in front, G at the end, W's kind of facing each other, canceling out. What that means is I want to add how fast Mr. Jack swims relative to the water with how fast the water flows relative to ground. But remember, they're not in the same direction. So we've seen this in one other question where we're going to have to use Pythagoras or possibly component method. I think Pythagoras in this one because it's straight north, straight east, but you may have to use component method or sine law, cosine law, something like that if they're not nice right angles. So we can think of it like that. When I actually think of these questions, I kind of think of it like, here's Mr. Jack. He is swimming in the water, and the water flows over the ground. So I think of these little pictures. This is, let's say, let's put it on this side, this is Jack, this is the water, this is the ground. Anytime you talk about the velocity of one object, it's always with respect to the object that it flows over, unless they tell you otherwise. So for example, we say, how fast is Jack going relative to the water? That's that 6.5 meters per second. We also talk about how fast the water is flowing relative to ground. That's 12 meters per second. Water to ground, Jack to water. Let's get rid of this equal sign. If I add those two things together, this is what we're seeing from the subscript equation. If I add those two things together, what I end up with is top level to bottom level. Okay, so when I add those two together, I equal Jack to ground. That's what we're talking about here, Jack to ground. So when I think of this, I don't actually think of the subscript equation too often unless I'm doing component method. I kind of think of these little pictures, whatever helps you out. If the pictures help, great. If the subscript equation helps, great. What we're doing here then, we just have to decide which item goes where. This is Jack to water. This is 6.5. Over here, we've got water to ground, and that is 12 meters per second. Okay, so they ask us some other things before they actually ask us this velocity over here. This is part C, velocity of Jack to ground. Before we get there, they ask us some other things. How long does it take him to cross the river? This is kind of like a subway type question if you're walking across the subway car. If your distance that you're given is in the straight north direction, then you need a corresponding velocity in the straight north direction. So when I do part A, velocity, displacement over time, we're looking for time. So time, displacement over velocity. Displacement, 45 meters. That would be Mr. Jack's displacement relative to water, or you could think of it as like in the y direction. And this is in the y direction, so you can think of it like dy and vy. Things won't always be nicely in that direction. Somebody could be aiming on an angle, but you can think of it here like that. Velocity, 6.5. I divide those and I get 6.923. Time, approximately 6.9 seconds. Okay, so that's how long it takes him to get to the other side. But when he gets to the other side, he does not end up at the tree. He also gets pushed down this way. So for the same 6.9 seconds, the water is pushing him this way. This is a bit like projectile motion. How much time do you spend going this way and how much time do you spend going this way? Well, it's the same time, but you do cover different distances or displacements, I guess. Okay, so how far from the tree does he end up? He ends up somewhere over here. What is this distance? Again, you can think of it like, what is dx? Okay, so v is d over t. You could say d is v times t. In this case, again, it's x direction, which means I need an x direction velocity. Velocity in the x direction is water to ground. It's 12. Time, let's use the unrounded, 6.923. And for this, we should get about 83.1, I guess, for sig digs. Should really just be 83 dx, 83 meters. This is his distance from the tree. Okay, so that's over here. How far away from the tree does he end up? He's 81 meters downriver. Find his velocity relative to the tree. Now we got a couple ways we can do this. You could just use this triangle. We've done this kind of thing before. We could use Pythagoras and some trig to find out this angle. The other thing that we could do is knowing the time. If we know this displacement, so for example, we know this is 45 meters in terms of displacement. This is 83.1 meters. We could use Pythagoras for that. I'd say I wouldn't, but you could use Pythagoras for that. Find out the displacement here along the hypotenuse, and then use the displacement and time, divide those to find out velocity. It's probably more work actually, but we could. So just so you know, there's often different ways that we could find these. In this case, what we're going to say is just using Pythagoras. VJG is the square root of 6.5 squared, 12 squared. That is approximately 13.6. We also need to find out this angle right here. Opposite over adjacent. This is about 62 degrees. So VJG as a vector, approximately 14 meters per second. So that's for sig digs. We could say north, 62 degrees east. And there we go. You can see the math in this question. There's not really hard math. I mean, we're doing a bit of division, we're doing a bit of Pythagoras and trig. The math isn't hard. It's setting up the diagram that really is, if anything is hard, that's the hard part. Once you get the diagram, then most of the math is pretty simple.